Question number 3. A negative particle is moving a velocity v enter to the region magnetic field B perpendicular to the particle velocity. What happened to the velocity and kinetic energy of particle? Explain your answer. So let's say you have a magnetic field B. This is magnetic field B, and you have a particle. Let's say this is a positive charge enter to the region's magnetic field B. So the particle have a force X on it. So according to you can use the left hand. So your thumb is direction of the finger, your first finger is direction of the B, and your second finger is direction of your V or speed of the particle. So the speed of particle is the straight line to the right, and direction of the B is into the page. So meaning that the angle between V and B is a 90 degree. So if you use the right hand, the direction of the force is outward. This is direction of the force. What happened to the velocity? So if the particle or positive particle enter to the region B, the velocity is changed, or we have a delta V here, because the direction of the particle after enter the regions B, the direction is not a straight line, but direction is follow to the circular path here. So this is direction after particle enter into the magnetic field B. So this is direction of the positive charge. So this is a circular motion, right? Circular motion. When the particle moving in the circular path here, so the particle have a acceleration. That's why the particle have a change of delta V. But the value of the speed is constant, right? So meaning if you calculate the kinetic energy E, half mv square, so the value of the V is speed is constant, but the direction of the particle change, that's the particle moving in a circular motion. Or we have a AC here. AC is a centripetal acceleration V square divided by R. So what happened to the velocity? Velocity is changed, right? Delta V, because direction of the particle change, and the kinetic energy is not changed because of the speed of the particle is constant. Next question number 3b. So this is the figure 4. So the question asks you, the first is figure show the rectangular carrying wire loop a free rotate about the vertical axis, and the magnetic field is 1.42 Tesla, and it is the distance, and this is current flow in the wire. So the first question asks you to calculate the magnetic force, magnetic force on the AB, on the wire AB. So when the current, the carrying conductor in the magnetic field B, so the wire have a magnetic force X on it. The force here is magnetic force on the wire is given by the B, magnetic field B, current flow, and the length of the wire. So now the question asks you A and B. So this is A and B. So the length of the wire here is 20 cm. The value of the B is 1.42, and the current flow is equal to the current is equal to 0.25 ampere, and the length here is 20 cm, convert to the meter is 0.2. So the force, magnetic force X on AB wire is equal to 0.071 Newton. And the next is what is direction? The force X on the AB. You can use the left hand. So this is your thumb is the force, and the first finger is direction of the B, and the second finger is direction of the L or I, right? So the direction of the B is this is the direction of the B is out of the page, and this is direction of the current flow I to the right. So meaning if you use the left hand, the direction of the force is downward. This is direction of the force by using the left hand. Next question asks you when the AB rotate to upwards, rotate to the upward, when the angle theta between B and L is equal to 0. So meaning the equation here, FB, force external on the AB, is given by the BIL sine theta. For question number 1, the sine theta here is equal to 1, because sine 90, because direction of the B to the out of the page and direction of the L to the right. So meaning this is angle is a 90 degree. So now if the AB rotate to 90 degree here, meaning the angle between B and L here is equal to 0. So this is sine 0. Sine 0 degree is equal to 0. So meaning the force X on AB is equal to 0. Number 3C, two long wires, straight parallel wire placed to 0.2. So let's say you have wire 1 and we have wire 2, and the distance between the two wire here is 0.2 meter, and each wire carrying the 1.5 ampere. Let's say the direction to upward, this is 1.5 ampere currents, and this is also I is a 1.5 ampere current. Let's see, this is I1 current 1, and this is I2, same direction to upward, right? Now the calculate number 1, calculate the magnitude of the force per unit length of the wire. So the force per unit length, so according to the equation, is given by the nu naught I1 I2 over 2 pi d. So we need the force per unit length. So I1 current flow 1.5 ampere produce magnetic field B. If you use the right hand, the direction of the B is this is out of the page, right? So this is into the page. So the same if you use the right hand here, for the second wire, direction of the B is this is right hand, so meaning this is out page, and here is this part is into the page. So meaning at the center here, you have 2B. The first B is come from the magnetic field by the wire 1, and the second B is produced by the wire 2. But the direction for the wire 1, I1 is into the page, right? And the second wire, the direction of the B is out of the page. Okay, what is a magnetic field? Force per unit length. So the first question is first per unit length. So the nu naught is constant, 4 pi exponent minus 7, and the I1 and I2 is 1.5, the same magnitude, and D is a distance between the two wire is equal to 0.2, right? So this is a 0.2 meter, and this is a 2 pi. So the value of force per unit length is equal to 2.25 exponent minus 6. The unit is Newton per meter, right? Newton per meter, because this is Newton and this is L is length is meter. And number 2, what is the magnetic field at the midpoint between the wire? So this is the midpoint here. So at the midpoint here, because the wire have a same magnitude of I, the same magnitude of I, so if you look at the calculation for magnitude B is given by the mu naught I divided by 2 pi r. Because of the value of the, let's say this is B1 and this is the B2 is B produced by the wire 2 is also mu naught I divided by 2 pi r. So the value of the mu naught is the same value, the I is the same value, 1.5, 1.5, and the radius is at the wire to the midpoint is the same value meaning B1 is equal to B2. But the direction of the B1 into the page, right, into the page, and direction of the B2 is out page, meaning that this is opposite direction. So if you have a B1 is equal to minus, let's say you have a B2 because of direction, or meaning the total or net magnetic field B at the midpoint is equal to B1 plus minus B2, so this is equal to 0. That's why the answer is 0. Okay, number 3, what happened to the force on the wire if each wire carry the same current but in opposite direction? So the first situation here, two wires have the same direction, so meaning you have a attracting force here. Yeah? So if the current have a opposite direction, let's say upward and the second wire downward, so now the two wire have the force, but the direction of the force is repulsive force, right? So for the same direction, the two wire have a attractive force, and the two wire with the opposite direction, the force X on the wire is repulsive force. Thank you.